The video opens with a monolithic electric drive system. Installed on an aerodynamic boat hull, it starts with drawing geometric lines on EP's foam, covering it with fiberglass, and rolling on reinforced epoxy resin. A high-torque brushed DC motor is being welded. Notice the surrounding copper water cooling loop. The engineer uses a steel ruler and a pen to determine the exact thickness and profile on the foam board. The hull alignment cuts are carefully measured using a tri-square and cut precisely with a craft knife. The clear 2-part epoxy resin is weighed with absolute precision using a digital microscale. The hardener catalyst is vigorously mixed into the base resin to trigger the polymer chemical reaction. The resin mixture is spread evenly over the board surface with a foam roller. The material creates an adhesive network bond. Multiple foam boards are pressed tightly together using dead weight, from bricks to avoid air gaps. Now, here is the process of making a hot wire cutter. A wooden bar is drilled to attach a metal pivot pin. Bolts and washers are tightened to create a hinge mechanism combined with a tension spring. The hand drill continues to machine the holding clamp for the fast heating nichrome resistance wire. The spring maintains constant tension when the metal wire expands due to red-hot high temperatures. The heating power source is creatively supplied from the clamps of a high-intensity arc welding machine. This hot cutting tool goes through the foam block as easily as slicing through butter, completely eliminating friction. The sharp, beveled bow contour is taking shape, strictly following hydrodynamic principles. A thin wooden measuring stick is used as a guide to ensure the hot cut line is perfectly straight. The V-shaped bottom is being sloped symmetrically. This design helps part the waves and reduce water drag. Every edge is being delicately shaped with the hot wire, ensuring both sides of the hull achieve perfect balance. The cuts are carefully aligned, creating a narrow hull cavity, laying the foundation for a high-speed wave riding machine. Proceeding to reinforce with high-strength composite materials. Cross-woven fiberglass cloth completely wraps the foam core. Liquid epoxy resin is rolled deep into the woven fiber structure, creating an ultra-durable crystalline network bond. The resin saturation process is done carefully to squeeze out all air bubbles, yielding a glossy finish. The engineer trims off the excess fiberglass edges, ready for the hull structure's next coating layer. 2 additional side outrigger floats are integrated, turning the monohull design into a trimaran, a stable trimaran. The fiberglass cloth layer is then applied to the side floats, molding them into a single block with the main hull. An electric jigsaw is used to cut out a square hole, precisely on the flat foam deck of the central system. A small wooden mold, fiberglass wrapped and epoxy coated, will act as a waterproof box to protect the circuitry. Cured resin creates an independent compartment, fully isolating and protecting the components from short circuits. Now, diving deep into the mechanical drive section, the universal joints, locking pins are being removed with a hex key. The drive shaft and bearings inside the motor housing are disassembled to proceed with machining operations. The shaft component is mounted on the mechanical lathes chuck to accurately turn the outer profile. A handheld angle grinder is used directly on the lathe to grind the steel component at high speed. After grinding, the shaft is checked for clearance before being reassembled into the universal joint housing. A metal flange is mounted on the lathe to drill an exact centering hole for the shaft. The newly machined flange is securely bolted to the motor block using recessed hex screws. The engineer prepares a U-clamp and a steel ring, clamping them tightly on a vise for welding. The electric arc melts the metal, fusing the steel ring to the thick shaft sleeve with a deep penetrating weld. The core drive shaft is lubricated with grease and carefully threaded into the protective sleeve. An angle bracket is arc welded to the tube body, providing a solid anchor point for the steering system. The electric motor is directly connected to the universal joint of the drive shaft assembly that was just completed. The entire drive assembly is passed through the bulkhead hole into the hull's waterproof compartment. The pass-through point is sealed with fiberglass and red-tinted epoxy resin for absolute waterproofing. Moving on to the painting process, a gray primer coat is sprayed evenly using a pneumatic spray gun. The primed surface is meticulously sanded to create the best adhesion for the top coat. Masking tape is used to spray sporty patterns. Orange and blue create a strong visual effect. The shaft system is inserted into the stern bracket. A metal hinge is welded to secure the downward tilt angle. A layered rubber CV boot is slipped on to protect the joint, tightened with a hose clamp. A 3-blade brass propeller with a curved profile is screwed tightly onto the threaded shaft and locked with a nut. The flexible steel cable of the steering system is threaded through the guide tubes, routing through into the center cabin. Both cable ends are screwed onto the swivel base of the engine mount, allowing for propeller steering. Drill holes and screw in the steering wheel bracket. The cable turnbuckles are fine-tuned to achieve standard tension. The steering cable is wrapped around a bicycle hub. The smooth shaft is trimmed to fit the steering wheel. The hub shaft is tightened with a torque wrench to ensure smooth rotational movement without slipping. The water cooling system is being completed. A mini water pump and transparent silicone tubing are connected. Is mounted onto the steering wheel bracket to control the engine's RPM. The precast composite seat is securely installed on the steel frame, optimizing the driver's center of gravity. 4 high-capacity lithium battery packs with aluminum heat sinks are connected to the electronic circuit inside a sealed box. Engine activated. The universal joint transmits torque, spinning the propeller shaft at high speed. The cooling water circulates. Dryland testing is successful. The propeller blades slice through the air powerfully. The steering system responds quickly, ready for launch. Testing the steering angle on land shows the operating range of the universal joint is extremely flexible. The boat is officially launched into the water. The electric motor's torque pushes the trimaran to glide incredibly smoothly. The point of view camera angle shows a comfortable driving posture. Cool water is continuously pumped and circulated through the motor. The multi-hull design helps eliminate wave resistance, providing excellent stability when running at high speeds. The water pump runs continuously, shooting a stream of water out, proving the cooling system is operating perfectly. The engineer easily steers the boat. The steering wheel is light and responds extremely accurately via the pull cable system. Viewed from above, the acceleration of the electric boat is very good, cutting through waves smoothly without leaving much wake. The exposed universal joint drive system proves its durability and ability to transmit maximum power into the water. The drone angle showcases its ability to weave through obstacles, floating on the river incredibly smoothly. Surfing the waves with electric power is completely silent, opening up a green direction for sports boats. The second project begins with the appearance of two internal combustion engines and a pair of brass propellers. The material is still the familiar EPS foam, but much larger, preparing for a powerful twin-engine motorboat build. Sharp profile lines are drawn out. The engineers carefully use a knife to trim and shape the boat's bow. Unlike the previous project, this time packing tape is used to completely wrap the foam core. The taping process requires an absolutely flat surface. It will act as a film mold layer. Composite materials are prepared again, including fiberglass, polyester resin, and a quick curing catalyst. A large fiberglass sheet is spread evenly,
fully covering the foam mold surface sealed with tape. Liquid resin saturates the fiberglass under the roller, squeezing out air bubbles as the molding process takes place. The composite shell is completely cured. The engineer uses an angle grinder to accurately cut technical gaps. Starting to paint the boat hull, a layer of turquoise paint is rolled evenly on the outside to create a protective film. The interior cabin is accented with an orange tone, a striking contrast with the exterior. The heart of the boat, the two internal combustion engines, compact two-strokes, are having their starter covers removed. The engine mount reinforcement steel plates are measured. The small chain sprocket is arc welded to the drive shaft. The threaded shaft carrying the brass propeller is threaded through.
The locating hole under the hull, ready to receive power. The engineer proceeds to tack weld the engine mounts directly onto the hull's reinforced steel frame. The roller chain drive system is connected between the engine crankshaft and the propeller shaft. A bicycle hub is cut and shaped, then using a step drill bit to widen the metal center hole. A threaded steel shaft is welded solid to the hub, creating a load-bearing rotating base for the steering system. A sports steering wheel is tightly secured to the rotating base. High-strength core parachute cord is wrapped to serve as the steering cable. Two custom expansion chamber exhausts are installed onto the exhaust ports of the twin engine block to optimize power output. The throttle cable is carefully threaded through a retaining clip, connecting directly to the carburetor's lever. A central throttle control lever is welded into place. Two colored buttons serve as engine kill switches. 5 silicon fuel lines are connected from the custom-built fuel tank made of PVC pipe straight to the two carburetors. Testing the throttle butterfly spring and the smooth movement of the steering cable spool right under the steering column. A large single rudder is mounted at the rear of the boat, ED directly to the pull cables from the steering wheel. The pull cables are finely adjusted, allowing the rear rudder to swing left and right in perfect sync with the steering movements. The mechanical steering system via the cable spool operates smoothly. Two independent propellers are ready to spin and tear through the water. A close-up of the engine bay shows the twin engines placed symmetrically with the chain drive, aggressive exhausts, and the central fuel tank. The overall architecture of the motorboat is incredibly imposing. The mechanical cable system is laid out in a highly logical manner. The completed twin-engine boat features a practical combat-ready design language, fully showcasing the beauty of raw primitive mechanics. In the water, the roar of the two-stroke engines echoes out. The twin propellers create powerful thrust, propelling the boat forward. The hull glides across the water's surface with absolute balance, cutting through waves smoothly, thanks to the split bow design. Tight turns are executed incredibly smoothly. The large area rudder, combined with the twin propellers, maximizes turning force. As speed continues to increase, the two exhausts release smoke, showing smooth coordination between the throttle and the steering system. The massive torque from the two internal combustion engines helps the boat accelerate spectacularly across the river. The frame shifts to a camera angle from a first-person perspective, clearly capturing the vibrations and powerful sound. The steering wheel is turned sharply, and the boat leans smoothly into the corner, proving the stability of its hydrodynamic design. The dual thrust is distributed evenly across both sides of the hull, eliminating any twisting motion. When operating at high intensity, the fabrication project concludes beautifully, an excellent testament to mechanical creativity and craftsmanship.